Hello everyone. Today, let me go over exam review sheet 3. Suppose $4,000 is deposited into a bank, offering an annual interest rate of 8%. So we know that the principal is $4,000 and the annual interest rate is 8%. If we convert 8% to decimal number, that's 0.08. That's what's given. Part A. If the interest is compounded quarterly, what's the account balance after 5 years? So if the interest is compounded quarterly, that means we compound interest 4 times a year. And we're looking for account balance after 5 years, times 5 years. For compound interest, the formula is amount equal to the principal times 1 plus R over N to the power of NT. Here R is the annual interest rate. N is number of times we compound interest in a year. T is number of years. Then plug in. The principal is 4,000. R is 0.08. N is 4 to the power of NT. N times T, 4 times 5 is 20. Then use calculator. When I type this into my calculator, I get $5,943.79. In general, for money, we round to the nearest cents. So the account balance after 5 years is $5,943.79. That's part A. Part B. If the interest is compounded monthly, then it's 12. Because a year has 12 months, we compound interest 12 times a year, then it's 12. What's the account balance after 9 years? So T is 9. T represents number of years. We're looking for the account balance, which is the amount in the account. Using the same formula. For compound interest, we have 1 P times 1 plus R over N to the power of NT. Then plug in. Principal is 4,000. Annual interest rate is 8%. N is 12. We compound interest 12 times a year to the power of NT. That's 12 times 9. Then use calculator. In my calculator, I get $8,198.12. For money, round to the nearest cents. That's the account balance after 9 years. Part C. If the interest is compounded continuously, what's the account balance after 12 years? Now, for continuously compound interest, the formula is a little different. In this problem, we know that the time is 12 years. We're looking for the account balance. For continuous compound interest, the formula is A equal to P times e to the power of RT. That's the formula for continuously compound interest. Account balance is the amount is principal times e to the power of RT. Here, P is 4,000. E is a constant times to the power of R times T. Here, R is the annual interest rate, 0.08. T is 12. Then plug this into the calculator. 4,000 times e to the power of 0.08 times 12. In my calculator, I get $10,446.79. That's the account balance after 12 years if the interest is compounded continuously. Part D. If the interest is compounded continuously, how long will it take the account balance to reach 15,000? So part D, we know that interest is compounded continuously. We're looking for time. How long does it take the account balance to reach 15,000? We're looking for time. How long does it take the account balance to reach 15,000? So using the same formula. For continuously compound interest, the formula is A equal to P times e to the power of RT. We know the account balance is 15,000. Principal is 4,000. That's what's given. Principal is 4,000. E to the power of RT. Here R is 0.08. That's what's given. We are looking for T. We don't know what T is. We're looking for time. So try to get T by itself. I can first of all divide both sides by 4,000. If I divide both sides by 4,000, I get 15,000 over 4,000 equal to e to the power of 0.08 t. And we know that 15,000 over 4,000. If I cancel 3 zeros from top and the bottom, I get 15 over 4. We try to get t by itself here. What I can do is I can apply ln on both sides. If we try to cancel e, apply ln to both sides. We get ln of 15 over 4 equal to ln of e to the power of 0.08 times t. On the right side here, by the law of logarithm, ln cancels e. ln cancels e. We get ln of 15 over 4 equal to 0.08 times t. Next, in order to get t by itself, we divide both sides by 0.08. We get t equal to ln of 15 over 4 over 0.08. Then use calculator. Take ln of 15 over 4 divided by 0.08. In my calculator, I get about 16.52. So it takes about 16.52 years. It takes about 16.52 years for an account to reach 15,000. So the time is about 16.52 years. It takes this much time for an account to reach 15,000. Problem number 2. Evaluate each of the following expressions. Part A. Log base 4 of 48 minus log base 4 of 9 plus log base 4 of 12. For logarithmic functions with the same base, we have to combine them together. We can first of all convert subtraction to division. So I can rewrite first two terms as log base 4 of 48 over 9 plus log base 4 of 12. Next, we can convert addition to multiplication. It can be rewritten as log base 4 of 48 over 9 times 12. Then simplify. Simplify this expression here. 48 over 9, I can divide top and bottom by 3. I get 16 over 3 here. I can divide top and bottom by 3. I get 16 over 3. Next, 12 divided by 3. Take 12 divided by 3. 12 divided by 3 is 4. Eventually it turned out 16 times 4. And 16 times 4 is 64. Log base 4 of 64. Now this expression asks 4 raised to what power is 64? This expression is asking 4 raised to what power is 64? And we know that 4 to the power 3 is 64. That means the answer is 3. Since 4 raised to power 3 is 64. So the answer is 3. It's the answer to part A. Part B. Log base 9 of 54 minus log base 9 of 4 plus log base 9 of 6. Very similar. When we see log functions with the same base, try to combine everything together. I can first of all convert subtraction to division. It can be rewritten as log base 9 of 54 over 4 plus log base 9 of 6. Next, we convert addition to multiplication. It can be rewritten as log base 9 of 54 over 4 times 6. Next, let's simplify this expression. We know that 54 over 4, I can divide top and bottom by 2. I get 27 over 2. Next, if I take 6 divided by 2, we know that 6 divided by 2 is 3. Eventually, it turned out 27 times 3. And we know that 27 times 3 is 81. Here, this expression is asking 9 raised to what power is 81? This expression is asking 9 raised to what power is 81? We know that 9 raised to the power 2 is 81. So the answer is 2. Since 9 raised to the second power is 81. Answer is 2. Part C. How can we evaluate log base cube root of 5 of 25? How can we evaluate this expression? This expression is asking cube root of 5 raised to what power is 25? This expression is asking cube root of 5 raised to what power is 25? Usually we use x to represent unknown number. This expression is asking cube root of 5 raised to what power is 25? We know that cube root of 5 can be written as 5 to the power of 1/3. Cube root of 5 can be written as 5 to the power of 1/3. 25 can be written as 5 squared. And on the left side here, 5 to the power of 1/3 times x to the power of x, it can be written as 5 to the power of 1/3 times x. If we compare left side and right side, you can see that their base are exactly the same, which means their exponent must also be the same. So 1/3 of x equal to 2. Here, if I multiply both sides by 3, it turned out x equal to 6, which means cube root of 5 to the power of 6 is 25. So the answer is 6. So log base cube root of 5 of 25 is 6. That's the answer to part C. Part D. How can we evaluate log base 3 of cube root of 81? How can we evaluate log base 3 of cube root of 81? This expression is asking 3 raised to what power is cube root of 81? This expression is asking 3 raised to what power is cube root of 81? This expression is asking 3 raised to what power is cube root of 81? Here, on the left side, I leave it the way it is. It cannot be simplified. On the right side, we know that 81, it can be written as 3 to the power of 4. Then, cube root of 3 to the power of 4, it can be written as 3 to the power of 4 over 3. The exponent is the numerator. The index in the front is the denominator. For cube root of 3 to the power of 4, base 3 stays the same. The exponent become numerator. Index become denominator. So you get 4 over 3. 3 to the power of 4 over 3. Now if we match the left side and right side, you can see that their base are exactly the same. If the base is the same, exponent must also be the same. So s equal to 4 over 3. That's the answer to this expression. So log base 3 of cube root of 81 is 4 over 3. That's the answer to part D. Part E. What's log base half of cube root of 16? What's log base half of cube root of 16? This expression is asking a half raised to what power is cube root of 16? This expression is asking a half raised to what power is cube root of 16? We know that a half it can be rewritten as 2 to the power of negative 1. A half it can be rewritten as 2 to the power of negative 1. And 16 can be rewritten as 2 to the power of 4. 16 can be rewritten as 2 to the power of 4. On the left side, 2 to the power of negative 1 to the power of x, it can be written as 2 to the power of negative x. We can multiply the exponents by the law of exponents. We can multiply the exponents. Negative 1 times x is negative x. On the right side, cube root of 2 to the power of 4, it can be rewritten as 2 to the power of 4 over 3. Exponent become the numerator. Index become denominator. Now try to match the left side and right side. Since the base are exactly the same, the exponent must also be the same. So we have negative x equal to 4 over 3. Next, in order to get s by itself, I can multiply both sides by negative 1. Here s equal to negative 4 over 3. Which means log half of cube root of 16 equal to negative 4 over 3. That's an answer for this expression. F. How can we evaluate log base cube root of 4 of square root of 2 over a? How can we evaluate log base cube root of 4 of square root of 2 over a? This expression is asking cube root of 4 raised to what power is radical 2 over a? This expression is asking cube root of 4 raised to what power is square root of 2 over a? Let's simplify left side and right side first. On the left side, number 4 can be rewritten as 2 squared. On the right side, square root of 2 that can be written as 2 to the power of half. Number 8 can be rewritten as 2 to the power of 3. On the left side here, cube root of 2 squared, it can be rewritten as 2 to the power of 2/3. Exponent is the numerator. Index is the denominator. When we write, exponent become numerator. Index become denominator. That's how we write radical in exponential form. Power x stays the same. On the right side, 2 of half over 2 to the power of 3. When we divide two numbers with the same base, keep the base the same, subtract exponents. Half minus 3 is negative 5 over 2. If we subtract, half minus 3 is negative 5 over 2. Next, on the left side, we have 2 to the power of 2/3 to the power of x. By the law of exponent, we can multiply 2/3 and x. So we get 2 to the power of 2/3 times x equal to 2 to the power of -5/2. Here, since the base are exactly the same, the exponent must also be the same. We have 2/3x equal to -5/2. In order to get s by itself, I can divide both sides by 2/3. In order to get s by itself, I can divide both sides by 2/3. So here x is -5/2 divided by 2/3. Divide by 2/3 is the same as multiply by its reciprocal. Dividing by 2/3 is the same as multiply by its reciprocal. So we get -5/2 times 3/2. S equal to -15/4. That's the answer to this expression. That's the answer to this expression. -15/4. Part G. How can we simplify radical 3 to the power of log base 3 of 5? Here, the base is almost the same, but they are not exactly the same. In order to simplify this expression, we try to make the base the same. Then use the formula a to the power of log base a of x equal to x. We can simplify this expression. So try to make the base the same, then use this formula to simplify. First of all, square root of 3 can be written as 3 to the power of half. Then, by law of exponent, this expression can be rewritten as 3 to the power of half of log base 3 of 5. Next, by law of logarithm, we can bring this coefficient back as exponent. So we get 3 to the power of log base 3 of 5 to the power of half. By law of exponent, by law of logarithm, we can bring the coefficient back as exponent. Then, using this formula, a log base 3 of x equal to x. Here, a cancels log base a. Similarly, 3 cancels log base 3. We get 5 to a half. We know that 5 to the power of half can be rewritten as square root of 5. That's an answer to this expression. H. How can we simplify? 1/2, a half to the power of log base 2 of 9. Similarly, we try to make the base the same. In order to use this formula, we try to make the base the same. Here, a half can be written as 2 to the power of -1. Then, by the law of exponent, this expression can be written as 2 to the power of -1 times log base 2 of 9. Then, by the law of logarithm, we can bring the coefficient back here as exponent. I get 2 to the power of log base 2 of 9 to the power of -1. Then, by this formula, a log base a of x is x. That means a cancels log base a. So here, 2 cancels log base 2. What's left is 9 to the power of -1. And we know that 9 to the power of -1 is 1/9. That's the answer to H. Number 3. Expand each of the following expressions. Part A. ln of square root of sy over z to the power 3 w squared. How can we explain this expression? First of all, I can convert division to subtraction. Write it as ln of square root of sy minus ln of z to the power 3 w to the power 2. I can first of all convert division to subtraction. Next, to simplify each part individually. Simplify each part individually. For the first part, square root of sy can be written as sy to the power of 1 over 2. Next, in the first term, I can bring exponent to the front. I get half of ln of sy. For the second half here, I can convert multiplication to addition. In the second half here, I can convert multiplication to addition. Write it as ln of z cubed plus ln of w squared. So in the first term, I bring exponent to the front. In the second term, I convert multiplication to addition. Next, in the first term, I convert multiplication to addition. Write it as ln of x plus ln of y. In the second term here, in the first term here, I convert multiplication to addition. Write it as ln of x plus ln of y. In the second term, I bring exponent to the front. Write it as 3 ln of z plus 2 ln of w. I bring exponent to the front. Then, in the first parenthesis, I distribute half. I get half of ln of x plus half of ln of y. In the second parenthesis, I distribute negative sign. I get negative 3 ln of z minus 2 ln of w. That's how I explain this expression. Part B. Expand log of x plus y to the power 3 over ab squared. First of all, I can convert division to subtraction. Write it as log of x plus y to the power 3 minus log of ab squared. I can first of all convert division to subtraction. Next, I can bring exponent to the front. I get 3 log of x plus y. Bring 2 to the front, I get 2 times log of ab. Now, in the first term, we get log of a plus b. That cannot be simplified. I leave it the way it is. Log of x plus y, that cannot be simplified. I leave it the way it is. In the second term, I can convert a times b, convert multiplication to addition. I get log of a plus log of b. Here, convert multiplication to addition. Then leave the first term the way it is. I get 3 log of x plus y. Distribute negative 2. In the second parenthesis, distribute negative 2. I get negative 2 log a minus negative 2 log b. That's how I explain this expression. Part C. Expand the expression log base 5 of a squared b to the power 4 over cube root of cd to the power 4. Let's expand this expression. First of all, I can convert division to subtraction. Write this log base 5 of a squared b to the power 4 minus log base 5 of cube root of cd to the power 4. Next, in the first term, I can convert multiplication to addition. I get log base 5 of a squared plus log base 5 of b to the power of 4. In the second term, cube root can be rewritten as cd to the power of 4 to the power of 1/3. Cube root can be rewritten as power of 1 over 3. Next, bring exponent to the front. I get 2 log base 4 of a plus 4 log base 4 of b minus 1/3 of log base 5 of cd to the power of 4. Bring exponent to the front. Next, the first term and second term cannot be simplified anymore. We leave it the way it is. In the third term, I can convert multiplication to addition. I get 2 log base 5 of a plus 4 log base 5 of b. Leave the first two terms the same. In the third term, convert multiplication to addition. I get log base 5 of c plus log base 5 of d to the power of 4. Next, I can bring exponent to the front. In the last term here, bring exponent to the front. So everything else stays the same. Bring exponent to the front. I get 4 log base 5 of d. Next, distribute negative 1/3. I get 2 log base 5 of a plus 4 log base 5 of b minus 1/3 of log base 5 of c minus 4/3 of log base 5 of d. That's the final answer. Part D. We have log base 2 of square root of a plus b over x to the power of 3, y to the power of 5. First of all, square root can be rewritten as a plus b over s cubed y to the power of 5. Square root can be rewritten as power of 1 over 2. Next, I can bring exponent to the front. I get half of log base 2 of a plus b over s to the power of 3 y to the power of 5. Next, I can convert division to subtraction. I get half of log base 2 of a plus b minus log base 2 of s cubed y to the power of 5. In the first term, we get log base 2 of a plus b. That cannot be simplified, so I leave it the way it is. The first term cannot be simplified, so I leave it the way it is. In the second term, I can convert multiplication to addition. I get log base 2 of s cubed y to the power of 5 plus log base 2 of y to the power of 5. Next, I can bring exponent to the front. I get half of log base 2 of a plus b minus 3 log base 2 of x plus 5 log base 2 of y. Next, distribute negative sign. I can distribute negative sign to the parentheses. I get half of log base 2 of a plus b minus 3 log 2 of x plus 5 minus 5 log base 2 of y. Next, distribute half. Distribute half to all these three terms. I get half of log base 2 of a plus b minus 3 half of log base 2 of x minus 5 half of log base 2 of y. That's how we expand this expression. And that's the final answer. Next, number 4. Rewrite each of the following expressions as a single logarithm. Part A, we have 2 ln of x minus 4 ln of y plus 3 ln of z. First step, if there's a coefficient in the front, we first of all bring coefficient back as exponent. So it can be written as ln of x squared minus ln of y to the power of 4 plus ln of z cubed. First step, in front of log b function, if there's a coefficient, bring it back as exponent. Next, group all positive terms together and group all negative terms together. Here we have two positive terms. The first term and last term, they are positive terms. Group the positive terms together and group the negative terms together. That's the only negative term. Put it on the back. So I group ln of x squared plus ln of z cubed together and move the negative term to the back. This is a negative term. Move it to the back. Next, convert addition to multiplication. For the first two terms, convert addition to multiplication. It can be written as ln of x squared times z cubed minus ln of y to the power of 4. Next, convert subtraction to division. I get ln of x squared z to the power of 3 over y to the power of 4. That's how I combine everything together as a single logarithm. Part B. 1/3 of log of a minus 1/2 of log of b minus 5 log c minus 1/2 log d. First step, if there's a coefficient in front of logarithm, bring it back as exponent first. Bring the coefficient back as exponent first. I get log a to the power of 1/3 minus log b to the power of 1/2 minus log c to the power of 5 minus log d to the power of 1/2. And we know that power of 1/3 is the cube root. Power of 1/2 is square root. Power of 5 I leave in the way it is. Power of 1/2 is square root. Next, group all positive terms together and all negative terms together. There's only one positive term, put it in the front. There are 3 negative terms, put it on the back. For these 3 negative terms, I can pull out their negative sign. I get negative log square root of b plus log c to the power of 5 plus log square root of d. For these 3 negative terms, pull out negative sign. I get log square root of b plus log c to the power of 5 plus log square root of d. Next, in the parentheses, convert addition to multiplication. I get log cube root of a minus log of square root of b times c to the power of 5 times square root of d. Next, convert subtraction to division. Convert subtraction to division. I get log of cube root of a over square root of b times c to the power of 5 times square root of d. And for the final answer, in the denominator, we can see that b and d, they are both under square root. So it can be written as square root of bd times c to the power of 5. Leave the numerator the same. In the denominator, we get square root of b and square root of d. We can put both of them under the same square root. Put both b and d under the same square root. That's the final answer. I combine this expression together into a single logarithm here. Part C. We have 5 log base 3 of x minus 4 log base 3 of y minus half log base 3 of z. So to combine everything together into a single logarithm. First step, if there's a coefficient in front of logarithm, bring it back as an exponent first. So I get log base 3 of x to the power of 5 minus log base 3 of y to the power of 4 minus log base 3 of z to the power of half. And we know that z to the power of half, it can be written as log base 3 of square root of z. Next, group all positive terms together and all negative terms together. There's only one positive term, I leave it in the front. There are 2 negative terms, I put it in the back. I get log base 3 of x to the power of 5 minus these 2 terms. Since both terms are negative, if I pull a negative sign, I get log base 3 of y to the power of 4 plus log base 3 of square root of z. Since both terms are negative, if I pull a negative sign, it becomes a digit in the middle. Next, in the parentheses, convert addition to multiplication. I get log base 3 of y to the power of 4 times square root of z. Next, convert subtraction to division. I get log base 3 of x to the power of 5 over y to the power of 4 times square root of z. That's how I combine this expression into a single logarithm. Part D. We have 5 plus 3 log base 7 of a minus 2 log base 7 of b minus 4 log base 7 of c. We try to write everything together as a single logarithm. But in the first term, there's no logarithm. What can we do here? In the first term, there's no logarithm. What can we do here? We know that there's a formula that says log base a of a to the power of x always equal to x. That means for number 5, I can write it as log base a of a to the power of 5. Number 5 can be written as log base a of a to the power of 5 by this formula. Log base a of a to the power of x is always x. That means for any real number x, 5 can be written as log base a of a to the power of 5. So here, since the base is 7, I can write 5 as log base 7 of 7 to the power of 5. since 4 is log base A of A to the power of 5. If I choose the base to be 7, I get log base 7 of 7 to the power of 5. That's how I write number 5 as a logarithmic function with base 7. Next, for the other terms, if there's a coefficient in the front, bring it back as exponent. I get log base 7 of A to the power of 3. Second term, I get log base 7 of B to the power of 2. And the third term, I get log base 7 of C to the power of 4. Next, we group all positive terms together and all negative terms together. We get log base 7 of 7 to the power of 5 plus log base 7 of 8 to the power of 3 minus, for these two terms, since they are both negative, if I pull out negative sign, I get log base 7 of B squared plus log base 7 of C to the power of 4. So for these two terms, if I pull out negative sign, I get addition in the middle. Next, convert addition to multiplication. In the first parenthesis, I get log base 7 of 7 to the power of 5 times A to the power of 3. In the second parenthesis, I get log base 7 of B squared C to the power of 4. And finally, convert subtraction to division. We get log base 7 of 7 to the power of 5, A to the power of 3, B squared C to the power of 4. For the final answer, use calculator, find 7 to the power of 5. That means 7 times 7 times 7 times 7 times 7. 5 sevens multiplied together. In my calculator, I get 16,807. A to the power of 3 over B squared C to the power of 4. That's the final answer. That's how I combine this expression together as a single logarithm. Next problem, solve each of the following equations. Part A, solve an equation log base 9 of x minus 5 plus log base 9 of x plus 3 equal to 1. We try to solve this equation for x. First of all, I can convert addition to multiplication. It can be written as log base 9 of x minus 5 times x plus 3 equal to 1. This expression, it means 9 to the power of 1 equal to this expression. This equation, it means 9 to the power of 1 equal to this expression. So that means x plus 5 times x plus 3 equal to 9 to the power of 1. This equation, it means 9 to the power of 1 equal to this expression. So it can be rewritten as x minus 5 times x plus 3 equal to 9 to the power of 1. Next, let's multiply everything out. If I multiply everything out, I get x squared plus 3x minus 5x minus 15 equal to 9 to the power of 1. 9 to the power of 1 is 9. If I combine like terms, I get x squared minus 2x. Subtract 9 from both sides, I get negative 24 here. Next, if I factor, I get x minus 6 times x plus 4. If I solve an equation for x, I get x minus 6 equal to 0 and x plus 4 equal to 0, which means s equal to 6 and s equal to negative 4. Now, for logarithm equation, we always have to check the answer. For logarithm equation, we always have to check the answer. If I plug in 6 minus 5 is positive, that's okay. If I plug in 6 here, 6 plus 3 is also positive, so this answer is okay. If I plug in 6, both answer in the logarithmic function is positive, That's okay. If I plug in -4, -4 minus 4 is -9. That's invalid. If I plug in -4 here, -4 plus 3 is also negative. That's invalid. This number here cannot be negative. -4 must be rejected. Logarithmic function can only take positive numbers. If the number inside the parentheses is negative, the answer must be rejected. If I plug in -4, I get -9 and -1 here. -4 must be rejected. So the only solution here is x equals 6. Part B. Solve an equation. Log of x plus log of x plus 3 equal to 1. First of all, I can convert addition to multiplication. It can be written as log of x times x plus 3 equal to 1. And we know that for logarithmic function, if there's no base, we assume the base is 10. That's called a common log. If there's no base, we assume the base is 10. That's called a common log. For logarithmic function, if there's no base, we assume the base is 10. That's called a common log. Log base 10 of x times x plus 3 equal to 1. That means 10 to the power of 1 equal to this expression. That means 10 to the power of 1 equal to this expression. So we have x times x plus 3 equal to 10 to the power of 1. This expression means 10 to the power of 1 equal to this expression. So x times x plus 3 is 10 to the power of 1. Next, on the left side, if I distribute, I get x squared plus 3x. On the right side, 10 to the power of 1 is 10. Next, I can bring 10 over. If I bring 10 over, positive 10 becomes negative 10. Next, factor. I get x plus 5 times x minus 2 equal to 0. Which means either x plus 4 is 0 or x minus 2 is 0. Solve the equation for x. I get x equal to -5 and x equal to positive 2. Now, for logarithmic equation, we have to always check the answer. If I plug in -2, that's negative. If I plug in -5, that's negative. If I plug in -5 here, -5 plus 3 is also negative. Since logarithmic function cannot take negative numbers, -5 must be rejected. If I plug in 2, that's positive. 2 by itself is positive. If I plug in 2 here, 2 plus 3 is 5. That's also positive. So this answer is valid. That's the only solution, x equal to 2. -5 must be rejected. Part C. We have e to the power of 2x plus 3e to the power of x equal to 10. I can first of all bring 10 over. So this equation can be rewritten as e to the power of 2x plus 3 to the power of x minus 10 equal to 0. Now, how can we solve this equation here? For this equation, we can first of all make one substitution. If I let u be e to the power of x, then if I square both sides, u squared will be e squared, e to the power of x squared, which means u squared is e to the power of 2x. E to the power of x squared is e to the power of 2x. We multiply an exponent. If I substitute here, e to the power of 2x is u squared. E to the power of x is u. Then I can factor. If I factor, I get u plus 5 times u minus 2 equal to 0. which means it's either u plus 4 equal to 0 or u minus 2 equal to 0. If I solve both equations individually, I get u equal to negative 5 and u equal to positive 2. And we know that here u is e to the power of x. Plug it back, we get e to the power of x equal to negative 5 and e to the power of x equal to 2. In the first equation, we know that exponential function cannot be negative. Exponential function is always positive, so it won't be 0, it won't be negative. This answer is impossible. It must be rejected. There's no solution here. It must be rejected. Since exponential function cannot be negative, it must be rejected here, and there's no solution from here. In the second equation, e to the power of x is 2. I try to get s by itself, so I can apply ln to both sides. I try to get s by itself, apply ln to both sides. On the left side, ln cancels e, I get s by itself. On the right side, I leave it the same, ln of 2. So that's an only solution to this equation. S equal to ln of 2. That's the only solution to this equation. Find d. E to the power of 2x minus a times e to the power of x plus 12 equal to 0. For this equation, do the same thing. Let's make one substitution here. If I let u be e to the power of x, then u squared will be e to the power of x squared, which means u squared can be written as e to the power of 2x. Then plug in, substitute. E to the power of 2x is u squared. E to the power of x is u. Then I can factor here. If I factor, I get negative 2, negative 6. Negative 2 times negative 6 is 12. And negative 2 plus negative 6 is negative 8. That means either u minus 2 is 0 or u minus 6 is 0. So if we solve each equation individually, we get u equal to 2 or u equal to 6. Then plug in, replace u with e to the power of x. We get e to the power of x equal to 2 or e to the power of x equal to 6. In the first equation, if we apply ln to both sides, we get ln of e squared equal to ln of 2. On the left side, ln cancels e, we get s by itself. On the right side, I leave in the weighties, ln of 2. In the second equation, do the same thing. We try to get s by itself, so apply ln to both sides. I get ln of e to the power of x equal to ln of 6. On the left side here, ln cancels e, we get s by itself. On the right side, leave in the weighties, ln of 6. So those are the solutions of this equation. There are two solutions. Part E, we have s squared times e to the power of x plus 2x times e to the power of x equal to 2 times e to the power of x. I can first of all bring 2 e to the power of x to the left side. First of all, bring 2 e to the power of x to the left side. If I bring this term over, it's positive term. If I bring over, it becomes negative term. We get x squared times e to the power of x plus 2x times e to the power of x minus 2 times e to the power of x. I can first of all bring 2 e to the power of x to the left side. When I bring over, positive term becomes negative term. Next, I can try to factor. If I factor, I can pull out the common factor e to the power of x. Pull out e to the power of x. After factoring, I set both of them equal to 0. That means it's either e to the power of x is 0 or x squared plus 2x minus 2 is 0. Either e to the power of x is 0 or x squared plus 2x minus 2 is 0. In the first equation, we know that exponential function cannot be 0. Exponential function is always positive. It cannot be 0 and it cannot be negative. So there are no solution here. It's rejected. There's no solution from the first equation. In the second equation, this is a quadratic equation. We can try to factor first. But it looks like it's not factorable. We can try to factor first. But it looks like it's not factorable. If it's not factorable, we can try to solve it using quadratic formula, or solve it by completing square. Let me solve it using quadratic equation here. We have a equal to 1, b equal to 2, c equal to negative 2. If I use quadratic formula, I have s equal to negative b plus or minus square root of b squared minus 4ac all over 2a. So you get negative 2 plus or minus square root of b squared minus 4 times a times c all over 2a. That's negative 2 plus or minus 2 squared is 4 minus 4 times negative 2 is negative a minus negative a. Double negative is positive. We get 4 plus a over 2. Square root of 4 plus a is square root of 12 over 2. And we know that square root of 12 can be noted as square root of 4 times square root of 3. Square root of 4 is 2. Square root of 3 cannot be reduced. Leave it how it is. So s is negative 2 plus or minus 2 square root of 3 over 2. Then divide. If I take negative 2 divided by 2, I get negative 1. Plus or minus 2 divided by 2 is 1. Okay, square root of 3. 2 square root of 3 divided by 2 is square root of 3. So there are two solutions. Either s is negative 1 plus square root of 3, or s is negative 1 minus square root of 3. There are two solutions to this equation. Next, we have 2 to the power of x equal to 5 to the power of x plus 2. How can we solve this equation for x? I can first of all apply ln to both sides. Next, by law of logarithm, I can bring exponent to the front. I get x times ln of 2 equal to x plus 2 times ln of 5. Next, we try to solve an equation for x. So on the right side, I can first of all distribute ln of 5. I get x ln of 2 equal to x times ln of 5 plus 2 ln of 5. Next, I move x ln of 5 from right side to the left side. When I move over, this is positive term. When I move over, it becomes negative term. Next, on the left side, I can factor power x. If I power x, I get x times ln of 2 minus ln of 5 equal to ln of 5. Then I can divide both sides by ln of 2 minus ln of 5. So the final answer, x is ln of 5 over ln of 2 minus ln of 5. Then use calculator. In my calculator, I get negative 3.5129. Part G. I have 3 to the power of x squared minus 3x equal to 1 over 9. 3 to the power of x squared minus 3x equal to 1 over 9. How can we solve this equation for x? If I rewrite the right side can be written as 1 over 3 squared. 1 over 9. 9 can be rewritten as 3 squared, which means we have 3 to the power of negative 2 on the right side. Now if we compare left side and right side, they have the same base, which means the exponent must be the same. So we have x squared minus 3x equal to negative 2. Next, I can bring negative 2 from the right side to the left side. If I move over, this is a negative term. If I move over, it becomes a positive term. I get x squared minus 3x plus 2 equal to 0. If I factor, I get x minus 1 times s minus 2 equal to 0. Which means either s minus 1 is 0 or s minus 2 is 0. Solve the equation, s is 1 and s is 2. There are two solutions to this equation. H, we have 4 to the power of s squared equal to 2 to the power of s plus 1. If I rewrite the left side, 4 can be rewritten as 2 squared. If I rewrite the left side, 4 can be rewritten as 2 squared, which means 2 to the power of 2s squared equal to 2 to the power of s plus 1. Since both left side and right side have the same base, the exponent must be the same. So we have 2s squared equal to s plus 1. If I bring everything to one side, to the left side, I have 2s squared minus x minus 1 equal to 0. If I factor, we can try to factor using the AC method. Here, A, B, C. That's A, that's B, that's C. If I factor using the AC method, A times C is negative 2. We can try to find two numbers that they multiply to be negative 2 and add to be negative 1. We can try to use negative 2 and positive 1. When we multiply, we get negative 2. When we add, we get negative 1. So, next, rewrite the middle term using these two numbers. It can be rewritten as 2s squared minus 2x plus 1x minus 1 equal to 0. Then factor by grouping. For the first two terms, I can pull out 2x. If I pull out 2x, I get s minus 1. For the third and the fourth term, the only common factor here is 1. If I pull out 1, I get x minus 1. Next, the common factor is s minus 1. If I pull out a common factor, what's left is 2x plus 1. That means either s plus 1 is 0 or 2x plus 1 is 0. Solve the equation for x. I get s equal to 1 or s equal to negative 1 over 2. Those are the solutions to this equation. Number 6. Sketch each of the following graphs. Please indicate the domain, range, asymptotes, and intercepts. Part A. The function is f of x equal to 2 to the power of negative x plus 3. In order to graph this function, let's first of all choose a parent function. For the parent function, we drop number 3, drop negative sign. So for the parent function, I choose y equal to 2 to the power of x. Since the base is more than 1, the graph is increasing. It looks like this. Since the base is more than 1, the graph is increasing. It looks like this. That's the graph of the parent function. Y equal to 2 to the power of x. It passes through 1 in the y-axis. Horizontal asymptote is the x-axis. That's the horizontal asymptote. So this is the parent function of y equal to 2 to the power of x. Next, if I change x from positive to negative, I flip the graph over the y-axis. If I change x from positive to negative, I flip the graph over the y-axis. So I get y equal to 2 to the power of 2, negative x. If I flip graph over, y-intercept stays the same. Horizontal asymptote also stays the same. Next, if I add 3 to this equation, if I add 3 to the function, I shift the graph 3 units up. If I add 3 to this function, I shift its graph 3 units upward. If I shift this graph upward, horizontal asymptote will be shifted at the same time. Horizontal asymptote will be shifted at the same time. This point is 1. If I shift the 3 units upward, it becomes 4. 1, 2, 3, 4. Horizontal asymptote was 0. If I shift the 3 units upward, it becomes 3. That's the graph y equal to 2 to the power of negative x plus 3. This point is 4. So based on this graph, we can see that the domain is a set of all real numbers from negative infinity to infinity. The range is a set of all y values from 3 to infinity, not including 3. There are no x-intercepts. Since this graph doesn't touch the x-axis, there are no x-intercepts. Y-intercept is 4. Y-intercept is 4. And for y-intercept, the x-coordinate is always 0. We write 0, 4. There's a horizontal asymptote at y equal to 3. There's a horizontal asymptote at y equal to 3. (6b). The function is 1 minus 1/3 of x plus 2. In order to graph this function, it can first of all be written as, this function can be rewritten as negative 1/3 to the power of x plus 2 plus 1. Its graph can be written as negative 1/3 to the power of x plus 2 plus 1. In order to graph this function, let's choose a parent function first. For the parent function, drop all numbers. If I drop negative sign, drop number 2, drop positive 1, what's left is 1/3 to the power of x. So I choose the parent function to be 1/3 to the power of x. Its graph looks like this. Since 1/3 is less than 1, it's decreasing from left to right. It's decreasing from left to right. Y-intercept is 1. Horizontal asymptote is the x-axis. That's the graph of the parent function. Next, if I make the entire function negative, I flip the graph over the x-axis. If I make the entire function negative, I flip the graph over the x-axis. If I flip the graph over the x-axis, positive 1 becomes negative 1. Horizontal asymptote stays the same. That's the graph of the function y equal to negative 1/3 of x. If I make the entire function negative, I flip the graph over the x-axis. Next, when I add 2 to x, I shift the graph 2 units to the left. When I add 2 to x, I shift the entire graph 2 units to the left. When I add 2 to x, I shift the entire graph 2 units to the left. So shift this graph 2 units to the left. When I shift the graph to the left and right, horizontal asymptote stays the same. So this is still the horizontal asymptote. This point is negative 1. If I shift it 2 units to the left, it becomes negative 1, negative 2. If I shift this graph 2 units to the left, it becomes negative 1, negative 2. Horizontal asymptote stays the same. That's the graph. Next, when I add 1 to the function, I shift this graph 1 unit upward. When I add 1 to the function, I shift this graph 1 unit upward. When I add 1 to the entire function, shift this graph 1 unit upward. This point here is negative 2, negative 1. If I shift it 1 unit upward, it becomes negative 2, 0. So this point here becomes negative 2, 0. Horizontal asymptote, it was 0 here. If I shift it 1 unit upward, it becomes 1. So that's the horizontal asymptote, y equal to 1. This point is here. So that's the graph, y equal to negative 1/3 of x plus 2 plus 1. Based on this graph, we can see that the domain is the set of all real numbers. Domain is the set of all real numbers from net infinity to infinity. Range is a set of all y values from 1 to negative infinity. Range is the set of all y values from 1 to negative infinity, which is from negative infinity to 1, not including 1. That's the range. And x-intercept is negative 2, 0. X-intercept is negative 2, 0. How about a y-intercept? How about a y-intercept? For y-intercept, we plug in 0 for x. For y-intercept, plug in 0 for x. For y-intercept, we plug in 0 for x. Y equal to f of 0, which is 1 minus 1/3 of 0 plus 2. We know that zero plus 2 is 2. 1/3 to the power of 2 is 1/9. 1 minus 1/9 is 8/9. So the y-intercept is 0, 8/9. That's the y-intercept. 0, 8/9. That's the y-intercept. And that's horizontal asymptote at y equal to 1. There's a horizontal asymptote at y equal to 1. Part C. F of x is ln of x minus 3 plus 2. In order to graph this function, let's first of all choose a parent function. For the parent function, I drop all numbers. I'll choose the function y equal to ln of x. ln of x is log of base e of x. We know that e is more than 1. E is about 2.718. E is more than 1. For logarithmic function, if the base is more than 1, it's increasing from left to right. It's increasing from left to right. X-intercept is 1. There are no y-intercepts. There's a vertical asymptote. There's a vertical asymptote at the y-axis. That's the graph of the parent function. Next, based on the parent function, graph this function here. First of all, when I subtract 3 from x, I shift the graph 3 units to the right. Shift the graph 3 units to the right. If I shift this graph 3 units to the right, 1 become 4. Vertical asymptote was 0 here. If I shift it 3 units to the right, it becomes 3. So vertical asymptote was 0 here. If I shift it 3 units to the right, it becomes 3. 1, 2, 3. That's the new vertical asymptote. This point was 1. If I shift it 3 units to the right, it becomes 4. And the graph stays the same shape. The graph stays the same shape. Next, if I add 2 to the function, I shift this graph 2 units upward. If I add 2 to this function, I shift its graph 2 units upward. Shift its graph 2 units upward. When I shift the graph up and down, vertical asymptote stays the same. This point was 4 here. If I shift it 2 units upward, it becomes 4, 2. If I shift this point 2 units upward, it becomes 4, 2. So that's the graph. Based on this graph, we can see that the domain is a set of all real numbers from 3 to infinity. The range is a set of all real numbers from negative infinity to infinity. It's all y values from negative infinity to infinity. There's no y-intercept, but there's an s-intercept here. There are no y-intercepts, but there's s-intercept here. For s-intercept, we set y equal to 0. That's the graph y equal to ln of x minus 3 plus 2. If I set y equal to 0, I get 0 equal to ln of x minus 3 plus 2. I can first of all bring 2 over. I get negative 2 equal to ln of x plus x minus 3. Next, in order to eliminate ln, apply function e on both sides. I get e to the power of negative 2 equal to e to the power of ln of x minus 3. Here, on the right side, e cancels ln. We get x minus 3. In order to get s by itself, I can add 3 to both sides. S equal to 3 plus e to the power of negative 2. So the s-intercept is 3 plus e to the power of negative 2, 0. That's the s-intercept. So this point here is 3 plus e to the power of negative 2. That's the s-intercept. So domain range, no y-intercepts. That's the s-intercept. And there's a vertical asymptote, which is s equal to 3. That's the vertical asymptote. Domain, range, intercepts, and asymptotes. Part D, graph of the function f of x equal to negative 2 times ln of x plus 1. How can we graph this function? Let's first of all choose the parent function. For the parent function, I can drop all numbers. What's left is ln of x. So I can choose the function to be y equal to ln of x. ln of x, that means log base e of x. E is the base here. Since e is more than 1, its graph is increasing from left to right. Its graph is increasing from left to right. S-intercept is 1. Vertical asymptote is 0. Vertical asymptote is the y-axis, which is s equal to 0. Next, if I add negative sign to the from, I flip the graph over the s-axis. If I make the entire function negative, I flip its graph over the s-axis. So it looks like this. X-intercept stays the same. Vertical asymptote also stays the same. Next, if I multiply the function by 2, I stretch its graph vertically by 2. Stretch its graph vertically by a factor of 2. I stretch its graph vertically by a factor of 2. The graph is y equal to -2 L1 of x. Stretch its graph vertically by a factor of 2. Stretch vertically by a factor of 2. Asymptote stays the same. X-intercept stays the same. Next, when I add 1 to x, I shift the graph 1 unit to the left. When I add 1 to x, shift the graph 1 unit to the left. Shift the graph 1 unit to the left. Vertical asymptote was 0 here. If I shift it 1 unit to the left, it becomes -1. That's the new vertical asymptote. And this point is 1. If I shift it 1 unit to the left, it becomes 0. That's its graph. Based on this graph, we can see that the domains accept all real numbers from -1 to infinity. The domains accept all real numbers from -1 to infinity. The range is accept all real numbers, all y's, from -infinity to infinity. The range is accept all y values from -infinity to infinity. That's the domain and range. The x-intercept is 0. Y-intercept is also 0. X-intercept is 0, 0. Y-intercept is also 0, 0. There's a vertical asymptote at s equal to -1. There's a vertical asymptote at s equal to -1. Number 7, part A. Suppose cosine theta is -2/3. And cosecant theta is less than 0. Find all trigonometric ratios. In order to find all trigonometric ratios, let's determine the quadrant for angle theta first. Here, cosine theta is -2/3, which means cosine theta is negative. We know that cosine function is positive in quadrant 1 and quadrant 4, negative in quadrant 2 and quadrant 3. If cosine theta is negative, that means angle theta either belong to quadrant 2 or quadrant 3. And we also know that cosecant theta is negative. We know that cosecant function is positive in quadrant 1 and quadrant 2, negative in quadrant 3 and quadrant 4. Since cosecant theta is negative here, angle theta belong to either quadrant 3 or quadrant 4. Here you can see that the common quadrant is quadrant 3. The common quadrant is quadrant 3. So angle theta belongs to quadrant 3. Here, since cosine theta is negative 2/3, then cosine of the reference angle, cosine of theta bar, will be positive 2/3. If we consider its reference angle, cosine of reference angle is always positive. So cosine of angle theta bar is 2/3. Next, let's draw a triangle based on the reference angle. Let's draw a triangle based on the reference angle. Let's call this angle theta bar. Cosine is always adjacent over hypotenuse. Let's adjacent, let's hypotenuse. One side is missing here. Next, use Pythagorean theorem for the missing side. Pythagorean theorem says a squared plus b squared equal to c squared. Let's call these three sides A, B, C. C is always hypotenuse. So A is 2, B is missing, C is hypotenuse. C is 3. A is 2, B is missing, C is 3. Plotting. 2 squared is 4. 3 squared is 9. Subtract 4 from both sides. B squared is 5. So B equal to square root of 5. That's the missing side here. Next, find all trigonometry ratios based on the reference angle. We'll fix the sign later. We'll fix the positive negative sign later. Let's find the trigonometry values for the reference angle first. We'll fix the plus minus sign later. So for sine theta, we have opposite over hypotenuse. Since that's the reference angle, we'll fix the sign later. We'll fix the plus minus sign later. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Cotangent is adjacent over opposite. Secant is hypotenuse over adjacent. Cosecant is hypotenuse over opposite. Next, let's fix the plus or minus sign. Angle theta lies in quadrant 3. Sine function in quadrant 3 is negative, same as cosecant function. Sine and cosecant, they are negative in quadrant 3. Cosine function in quadrant 3 is also negative, same as secant. Tangent in quadrant 3 is positive, same as cotangent. So for the final answer, let's sine, cosine, tangent, cotangent. For cotangent, if we rationalize the denominator, we get 2 over radical 5. Multiply top and bottom by radical 5. The final answer is 2 radical 5 over 5. Secant is okay. For cosecant, if we rationalize the denominator, we can multiply top and bottom by square root of 5. We get negative 3 radical 5 over 5. That's the trigonometry ratios for all 6 functions. 7b. Suppose tangent theta is negative 4. And sine theta is positive. Sine theta is positive. Find all trigonometry ratios. In order to find all trigonometry ratios, let's find the quadrant for angle theta first. Let's determine the quadrant for angle theta first. Since tangent theta is negative, we know that tangent function is positive in quadrant 1 and quadrant 3, negative in quadrant 2 and quadrant 4. Since tangent theta is negative, angle theta lies in quadrant 2 or quadrant 4. Now here, sine function is passive. We know that sine function is positive in quadrant 1 and quadrant 2, negative in quadrant 3 and quadrant 4. Here, since sine theta is positive, angle theta lies either in quadrant 1 or quadrant 2. Here, the common quadrant is quadrant 2. The common quadrant is quadrant 2. That means angle theta lies in quadrant 2. That means angle theta lies in quadrant 2. Next, let's find the trigonometric ratios for the reference angle first. Let's find the trigonometric ratios for the reference angle first. Since tangent theta is -4, that means tangent of the reference angle is +4. Tangent of the reference angle is always positive. And 4 can be rewritten as 4/1. Next, let's draw a triangle based on this. Assume the reference angle is here. Tangent is always opposite over adjacent. One side is missing here. We can use Pythagorean theorem. Pythagorean theorem says a squared plus b squared equal to c squared. Let's call these three sides A, B, and C. C is always hypotenuse. So here, C is unknown. A is 1, B is 4, C is unknown. Okay, 1 squared plus 4 squared equal to C squared. 1 squared is 1, 4 squared is 16. 1 plus 16 is 17. So C squared is 17. That means C is square root of 17. That's the missing side. Next, let's find the trigonometric ratios based on the reference angle. We will fix the plus or minus sign later. So for sine theta is opposite over hypotenuse. Cosine theta is adjacent over hypotenuse. We will fix the plus minus sign later. Tangent is opposite over adjacent. Cotangent is adjacent or opposite. Secant is hypotenuse over adjacent. Cosecant is hypotenuse over opposite. Here, angle theta belongs to quadrant 2. We know that sine function in quadrant 2 is positive, since cosecant function. Cosine function in quadrant 2 is negative, since secant function. Tangent function in quadrant 2 is negative, since cotangent function. Then for the final answer, try to rationalize the denominator. Here, sine theta is positive 4 over radical 17. If we rationalize the denominator, I can multiply top and bottom by square root of 17. It turned out 4 square root of 17 over 17. Cosine is -1 over square root of 17. If we rationalize the denominator, we multiply top and bottom by square root of 17. It turned out negative square root of 17 over 17. Tangent is -4 over 1. If we simplify, that's -4. Cotangent is -1 over 4, that's okay. Secant is negative square root of 17 over 1. It can be rewritten as negative square root of 17, that's secant. Cosecant is positive square root of 17 over 4. I can leave it the way it is. So that's all trigonometric ratios of angle theta. Number 8. Evaluate each of the following expressions without using calculators. Part A. We have sine of 5 pi over 4. In general, we can try to convert from radian measure to degree measure first. It'll be a little easier. Convert from radian measure to degree measure first, it will be a little easier. If we convert 5 pi over 4 from radian measure to degree measure, take 5 pi over 4 times 180 degree over pi. If we cancel pi from top and the bottom, what's left is 5 times 180 degree over 4. 180 over 4 is 45. 45 times 5 is 225 degree. So sine of 5 pi over 4 is the same as sine of 225 degree. And we know that 225 degree lies in quadrant 3. 225 degree angle lies in quadrant 3. For angle in quadrant 3, its reference angle is an angle itself minus 180. 225 minus 180 is 45 degree. That's the reference angle. We get sine 45 degree here. And sine function in quadrant 3 is negative. This angle theta, 225 degree angle, lies in quadrant 3. Sine function in quadrant 3 is negative. And we know that sine 45 degree, that's a special angle. Sine 45 degree is 1 over radical 2. If we rationalize the denominator, that's radical 2 over 2. That's the answer of sine 5 pi over 4. Part B. How can we evaluate tension of 11 pi over 3? We can first of all try to convert 11 pi over 3 from radian measure to degree measure. 11 pi over 3, if I multiply by 180 degree over pi, I can cancel pi from top and bottom. What's left is 11 times 180 over 3. I can divide the angles first. If I take 180 divided by 3, I get 60. 60 times 11 is 660 degree. So tension of 11 pi over 3 is the same as tension of 660. And we know that 660 is more than one cycle. 660 is more than one cycle. For angle more than one cycle, I can subtract angle by 360. That's a coterminal angle. 660 minus 360, I get 60 degree. I get 300 degree. That's the coterminal angle. That's the coterminal angle of 660. And here we know that 300 degree angle lies in quadrant 4. 300 degree angle lies in quadrant 4. For angle lies in quadrant 4, its reference angle is 360 minus the angle itself. For angle lies in quadrant 4, its reference angle is 360 minus the angle itself, which is 60 degree. And we know that tension function in quadrant 4 is negative. Tension function in quadrant 4 is negative. Tension 60, that's a special angle. Tension 60 is square root of 3. That's the answer of tension 11 pi over 3. Part C. How can we evaluate cosine of negative 5 pi over 6? I can first of all convert negative 5 pi over 6 from radian measure to degree measure first. If I take 5 pi over 6 times 180 over pi, I can first of all cancel pi. I get 5 times 180 degree over 6. Here, if I take 180 divided by 6, I get 30. 30 times 5 is 150. So 5 pi over 6 is the same as 150. 5 pi over 6 is negative 150. If an angle is negative, we try to find its positive coterminal angle. If an angle is negative, we try to find its positive coterminal angle. If I take negative 150 plus 360, I get positive 210. That's its positive coterminal angle. So cosine of negative 150 is the same as cosine of 210. And we know that 210-degree angle lies in quadrant 3. Cosine function in quadrant 3 is negative. Its reference angle, for angle in quadrant 3, its reference angle is the angle itself minus 180, which is 30 degrees. So cosine of negative 210 is negative cosine 30. Since cosine function in quadrant 3 is negative. And we know that cosine 30 is radical 3 over 2. Cosine 30 is negative radical 3 over 2. That's cosine of negative 5 pi over 6. Part D. How about cotangent of 7 pi over 6? We can first of all try to convert 7 pi over 6 from radian measure to degree measure. If I take 7 pi over 6 times 180 over pi, I can cancel pi first. I get 7 times 180 over 6. 180 over 6 is 30. 30 times 7 is 210. So, cotangent of 7 pi over 6 is 210. We know that 210-degree angle lies in quadrant 3. And cosine function in cotangent function in quadrant 3 is positive. Cotangent function in quadrant 3 is positive. Its reference angle, for angle in quadrant 3, its reference angle is the angle itself minus 180, which is 30. So for 210-degree angle, its reference angle is 30-degree angle. And we know that cotangent 30 is a special angle. Cotangent 30 is square root of 3. That's a special angle. Cotangent 30 is square root of 3. That's how we evaluate cotangent of 7 pi over 6. Part E. How about secant of negative 7 pi over 4? We can first of all convert 7 pi over 4 from radian measure to degree measure first. I can take 7 pi over 4 times 180 degree over pi. Cancel pi. What's left is 7 times 180 over 4. I can take 180 over 4 first. I take 180 divided by 4 first, then times 7. 180 divided by 4 is 45. 45 times 7 is 315. And we know that 7 pi over 4 is 315. That means negative 7 pi over 4 is negative 315. If an angle is negative, we can try to find its positive coterminal angle first. If an angle is negative, we can try to find its positive coterminal angle first. For negative 315, keep adding 360 until it becomes positive. Negative 315 plus 360, I get 45-degree angle. So the positive coterminal angle is 45 degrees. And secant 45, that's a special angle. Secant 45 is square root of 2, that's a special angle. Secant 45 is square root of 2. That's the answer. That's the final answer. F. How can we evaluate cosecant of 13 pi over 3? For 13 pi over 3, we can first of all convert from radian measure to degree measure first. Take 13 pi over 3 times 180 over pi. I can cancel pi from top and bottom. What's left is 13 times 180 over 3. Next, I can do division first, then multiply. 180 divided by 3 is 60. 60 times 13 is 780. So cosecant of 13 pi over 3 is the same as cosecant of 780. And we know that 780-degree angle is more than one cycle. If the angle is more than one cycle, you can keep reducing the angle. Take 780 minus 360. We get 420-degree angle. So that's the same as cosecant of 420-degree angle. But 420-degree angle is still more than one cycle. So keep reducing by 360. Take 420 minus 360. We get 60 degree. So for 420-degree angle, its coterminal angle is 60-degree angle. And we know that cosecant 60 is 2 over radical 3. For the final answer, if we rationalize the denominator, we can multiply top and bottom by square root of 3. So the final answer is 2 square root of 3 over 3. That's cosecant of 13 pi over 3. Part G. How can we evaluate inverse sine of negative 1 over radical 2? How can we evaluate inverse sine of negative 1 over radical 2? For inverse trigonometry functions, the rule is that if the function is inverse sine, tangent, or cosecant, I can directly pull out negative sign. But for cosine, cotangent, or secant, when I pull out negative sign, I must add pi in the front. For inverse sine, tangent, and cosecant, I can directly pull out negative sign. But for cosine, cotangent, and secant, when I pull out negative sign, I must add pi in the front. Here, for inverse of sine, if the inside is negative, I can directly pull out negative sign. I get negative inverse sine of 1 over radical 2. We know that sine 45-degree angle is 1 over radical 2, which means that's negative 45 degree. And we know that 45-degree angle, if I convert to radian measure, if I convert 45 degree to radian measure, that's negative pi over 4. In general, for inverse trigonometry functions, we write the answer in radian measure. For inverse trigonometry functions, we must write the final answer in radian measure. H. How can we evaluate inverse tangent of negative radical 3? So for inverse sine, tangent, and cosecant, if the inside is negative, I can directly pull out negative sign. If the inside is negative, I can directly pull out negative sign. I get negative inverse tangent of radical 3. We know that that's a special value in the table. Tangent 60-degree angle is radical 3. Tangent of 60-degree angle is radical 3. That means inverse tangent of radical 3 is 60-degree angle. If we convert 60-degree angle to radian measure, that's pi over 3. Next, how can we evaluate inverse cosine of negative 1 over 2? For inverse cosine of negative 1 over 2, if I pull out negative sign, I must add pi in the front. I get pi minus inverse cosine of 1 over 2. For inverse cosine, cotangent, or secant function, if I pull out negative sign, I must add pi in the front. And that's a special angle. That's a special value in the table. We know that cosine of 60-degree angle is 1 over vertical 2. Cosine of 60-degree angle is 1 over 2, which means inverse cosine of 1 over 2 is 60-degree angle. And in general, we must convert from degree measure to radian measure. 60-degree angle in radian measure is pi over 3. Then pi minus pi over 3 is 2 pi over 3. That's inverse cosine of negative 1 over 2. Next, how can we evaluate inverse cotangent of negative 1? We know that for inverse cosine, inverse cotangent, or secant functions, when I pull out negative sign, I must add pi in the front. So I get pi minus inverse cotangent of 1. We know that for cotangent function, number 1 is a special value on the table. Number 1 is a special trigonometry values. We know that cotangent of 45-degree angle is 1, which means inverse cotangent of 1 is 45-degree angle. So we get pi minus 45-degree angle. 45-degree angle in radian measure is pi over 4. 45-degree angle in radian measure is pi over 4. If I take pi minus pi over 4, I get 3 pi over 4. That's inverse cotangent of negative 1. Next, how can we evaluate sine of inverse tangent of vertical 2? How can we evaluate sine of inverse tangent of vertical 2? Sine of inverse tangent of positive 2. Here, let's make one substitution. Then the inside function. Let theta be the inside function. Since number 2 is not a special value for tension, number 2 is not a special trigonometry values for tension. So let's make one substitution here. Let theta be inverse tangent of 2. So I have sine of theta here. Since inverse tangent of 2 is theta, let theta be inverse tangent of 2. That means tangent theta is 2. That means tangent of theta is 2. And we know that number 2 can be rewritten as 2 over 1. If we draw a triangle for angle theta, tangent is always opposite over adjacent. Tangent is always opposite over adjacent. So 2 is an opposite, 1 is adjacent. One side is missing here. For the missing side, we can use Pythagorean theorem for the missing side. Let's call these three sides A, B, and C. We have A squared plus B squared equal to C squared. C is always the hypotenuse. A and B could be either side, but C must always be the hypotenuse. So here, A is 1, B is 2, C is missing. Let's try to find C. A is 1, B is 2, C is missing. Let's try to find C. I get 1 plus 4 equal to C squared. C squared is 5, which means C is square root of 5. That's the missing side. Now here we are looking for sine theta. Sine theta is always opposite over hypotenuse. Sine is always opposite over hypotenuse. So you get 2 over radical 5. That's how we evaluate sine of inverse tangent of 2. Next, how can we evaluate secant of inverse cotangent of square root of 5? Here, since square root of 5 is not special trigonometry values for cotangent function, we must make substitution. Let theta be the inner function. Let theta be inverse cotangent of square root of 5. If I plug in theta for the inner function, I get secant of theta. And here, since theta is inverse cotangent of square root of 5, we know that cotangent of theta must be square root of 5. And we know that Square root of 5 can be rewritten as square root of 5 over 1. Next, let's draw a triangle for angle theta. Cotangent is always adjacent over opposite. So vertical 5 is adjacent, 1 is opposite. One side is missing here. We can use Pythagorean theorem to find the missing side. Pythagorean theorem is always a squared plus b squared equal to c squared. Let's call these three sides a, b, and c. C is always the hypotenuse. Here, c is the missing side. So plotting a and b and solve for c. A is square root of 5. B is 1. C is missing. Square root of 5 square is 5. 1 square is 1. 5 plus 1 is 6. So you get c squared equal to 6. If I take square root, c is square root of 6. That's the missing side here. So for secant theta, the formula is hypotenuse over adjacent, vertical 6 over vertical 5, hypotenuse over adjacent. And for the final answer, if we rationalize the denominator, we multiply top and bottom by square root of 5. That's square root of 30 over 5. That's the final answer for secant of cotangent of vertical 5. And for the previous one, we also need to rationalize the denominator. I can multiply top and bottom by square root of 5. I get 2 square root of 5 over 5. That's the final answer. Number 9. Sketch each of the following graphs. Please indicate the amplitudes and the periods, if appropriate. Part A. The function is f of x equal to 3 cosine of x plus 2. Let's choose the parent function first. For the parent function, you can drop 2, drop 3. We choose cosine x as a parent function. So for the parent function, we choose y equal to cosine of x. The graph of cosine x looks like this. It starts from 1. It goes down first. Then bounce back. At 2 pi, bounce back to 1. In the middle, we have pi here. X-intercept is pi over 2 and 3 pi over 2. That's the graph of cosine function in the first period. That's the graph of cosine function in the first period. Here, lower bound is -1, upper bound is 1. Now, if I multiply cosine by 3, we stretch the graph vertically by 3. Stretch this graph vertically by 3. The new graph looks like this. If I stretch this graph vertically by a factor of 3, 1 becomes 3. -1 will be -3. 0 stays the same. Pi stays the same. 2 pi stays the same. Pi over 2 stays the same. And 3 pi over 2 stays the same. All these points stays the same. Then the graph stays the same shape. It goes down first. At pi, reach the minimum, and then bounce back. At 2 pi, it goes back to 3. That's the graph of y equal to 3 cosine of x. Next, if I add 2 to the function, I shift this graph 2 units upward. Next, if I add 2 to the function, I shift the graph 2 units upward. This number here is 3. If I add 2, 3 plus 2 is 5. This number here is negative 3. If I add 2, negative 3 plus 2 is negative 1. And this point stays the same. And we know that cosine function repeats itself. That's the cosine function. That's this cosine function. Its period is from 0 to 2 pi. Its period is 2 pi. Its amplitude is half of the distance from maximum to the minimum. Amplitude is half of the distance from maximum to the minimum. Here, maximum is 5, minimum is negative 1. 5 minus negative 1 is 6. The distance from 5 to negative 1 is 6. Half of 6 is 3. That's the amplitude. Period is 2 pi. Amplitude is 3. Part B. The function is f of x equal to 2/3 of sine of half of x. In order to graph this function, let's choose the parent function first. For the parent function, you can drop all numbers. What's left is sine x. So for the parent function, we choose y equal to sine x. Choosing this as a parent function. The graph of a parent function looks like this. Sine function starts from 0. It goes up first, go back to 0. Then it goes down. At 2 pi, go back to 0. What's in the middle is pi. At pi over 2, we reach the maximum. At 3 pi over 2, we reach the minimum. It varies between negative 1 and 1. That's the graph of the sine function in the first period. That's the graph of the sine function in the first period. Now, if I multiply the entire function by 2/3, if I multiply the entire function by 2/3, 2/3 is less than 1, so I shrink the function by the factor of 2/3. Shrink vertically by the factor of 2/3. If I shrink the graph vertically, 1 and negative 1, it becomes positive 2/3 and negative 2/3. If I shrink the graph vertically, 1 and negative 1 become 2/3 and negative 2/3. Everything else stays the same. That's 2 pi, that's pi. What's in the middle is pi over 2. That's 3 pi over 2. Sine function starts from 0. Goes up first, then goes down. Eventually go back to 0. That's a sine function. It's 2/3 of sine x. Next, if I multiply x by half, the reciprocal of half is 2. That means 2 is more than 1. That means we stretch the graph horizontally by a factor of 2. Reciprocal of half is 2. Reciprocal of half is 2. 2 is more than 1. So stretch the graph horizontally by a factor of 2. Next, stretch the graph horizontally by a factor of 2. The new equation is 2/3 of sine of half of x if I stretch horizontally by 2, maximum and minimum stays the same. Two pi times 2 will be 4 pi. Pi times 2 will be 2 pi. Pi over 2 times 2 will be pi. 3 pi over 2 times 2 will be 3 pi. So the graph starts from 0, goes up first, goes down to 0, then it goes down. It returns to 0 at 4 pi. That's the first period. And we know that sine function continues itself. Here we can see that the period of this graph is 4 pi. What's the amplitude? Here, amplitude is half of the distance from maximum to minimum. So here, maximum is 2/3, minimum is negative 2/3. That's the distance from maximum to minimum. Half of the distance from 0 to 2/3. Half of the distance from 0 to 2/3, which is 2/3. That's the amplitude of this function. Part C. How can we graph the function f of x equal to -2 times sine of 2 times x minus pi over 4? In order to graph this function, let's choose the parent function first. For the parent function, you can drop all numbers. Drop all numbers. What's left is y equal to sine x. Choose sine x as the parent function. Choose sine x as a parent function. The graph of the parent function looks like this. Sine function starts from 0, goes up first, goes back to 0, then goes down. It goes back to 0 at 2 pi. What's in the middle is pi. It reaches the maximum at pi over 2. It reaches the minimum at 3 pi over 2. Sine function is bounded by -1 and 1. That's the sine function in the first period. Next, if I multiply sine by 2 in the front, I stretch the graph vertically by a factor of 2. I stretch the graph vertically by a factor of 2. The new graph looks like this. Now sine function is bounded by -2 and 2. If I stretch it vertically, 1 becomes 2, -1 becomes -2. And the points in the x-axis stays the same. That's the graph of sine function. Next, if I multiply the sine function, if I add negative sign to the front, I flip the graph over the x-axis. The function is -2 sine x If I flip the graph over x-axis, positive 2 become negative 2, and negative 2 become positive 2. This point stays the same. 0, pi, 2 pi stays the same. So this curve is here. This piece is here. That's negative 2 sine x. That's y equal to negative 2 sine x. Next, if I multiply x by 2, reciprocal of 2 is half. Half is less than 1. So I shrink the graph horizontally. By a factor of half. Next, shrink the graph horizontally. By a factor of half. If I shrink the graph horizontally, half of pi is pi over 2. Half of 2 pi is pi. The graph looks like this. Half of pi is pi over 2. Half of 2 pi is pi. The graph looks like this. The graph stays the same shape. That's the graph. Y equal to negative 2 sine of 2x. When I multiply x by 2, reciprocal of 2 is half. So shrink the graph horizontally by a factor of half. Next, if I subtract x by pi over 4, I shift the graph pi over 4 to the right. For y equal to negative 2 times sine of 2x minus 4. When I subtract x by pi over 4, I shift the graph pi over 4 to the right. Shift pi over 4 units to the right. If I shift the graph pi over 4 to the right, 0 plus pi over 4 is pi over 4. Pi over 2 plus pi over 4 is 3 pi over 4. Pi plus pi over 4 is 5 pi over 4. The graph stays the same shape. That's the graph in the first period. Here you can see that the period is the distance from 5 pi over 4 to pi over 4. 5 pi over 4 minus pi over 4 is 4 pi over 4, which is pi. 5 pi over 4 minus pi over 4 is 4 pi over 4, and 4 pi over 4 is pi. Amplitude. Amplitude is half of the distance from maximum to minimum. That's the distance from maximum to minimum. Half of the distance is from 0 to 2. Distance from 0 to 2 is 2. That's the amplitude. And we know that sine function actually repeats itself. Sine function repeats itself. That's the graph of its function. Part D. How can we graph the function? F of x equal to tangent of 4 times x plus pi over a. Let's choose the pattern function first. In order to graph its function, let's choose the pattern function first. For the pattern function, we can drop all numbers. If we drop all the numbers, what's left is y equal to tension of x. That's the parent function. Tension function in the first period. Tension function in the first period is from negative pi over 2 to pi over 2. Tension function in the first period is from negative pi over 2 to pi over 2. That's the tension function in the first period. That's the tension function in the first period. We choose this as a parent function. Now, if I multiply x by 4, reciprocal of 4 is 1 over 4. 1 over 4 is less than 1. So we shrink the graph horizontally by a factor of 1 over 4. Shrink the graph horizontally by a factor of 1 over 4. Shrink the graph horizontally by a factor of 1 over 4. The graph looks like this. If I shrink horizontally by 1 over 4, negative pi over 2 times 1 over 4 is negative pi over a. Pi over 2 times 1 over 4 is pi over a. If I shrink horizontally, that's how the graph looks like. Next, when I add pi over a to x, I shift the graph pi over a units to the left. When I add pi over a to x, I shift the graph pi over a units to the left. Next, shift the graph pi over a units to the left. Shift this graph pi over a units to the left. Negative pi over a. If I shift pi over a units to the left, take negative pi over a minus pi over a. That's negative pi over 4. If I take pi over a minus pi over a, I get 0. This number is 0 here. 0 minus pi over a is negative pi over a. Then that's a new graph after I shift pi over a to the left. So based on this graph, we can see that for tension function, there's no amplitude. Its period. Its period is the distance from 0 to negative pi over 4, which is pi over 4. Its period is the distance from 0 to negative pi over 4, which is pi over 4. And also, for tension function, there are infinitely many such pieces. We have another piece on the left. And another piece on the right. There are infinitely many such pieces. That's the graph of this function. That's its period. Only sine and cosine has amplitude. The rest of the function doesn't have amplitude.